Our last unit was Unit 5, which had the underlying theme of fire. We covered 3 chapters in this unit, 18, 19, and 20. Anytime matter moves or changes in any way, energy is involved. You started this unit with the question, what is fire? You also looked at the question, where does energy come from and how can we best make use of it? You looked at the idea that heat is a process of energy transfer, and although heat is not a substance, it cannot exist independent of matter. To clarify any confusion with the term heat, you experienced heat transfer directly and acquainted it with the concept of system and surroundings. You found that heat transfer is a result of differences in temperature, and that cold is a sensation experienced when heat is transferred out of the body. Additionally, you looked at what occurs on the molecular level when heat is transferred, as well as what occurs to particles in terms of heat transfer during a phase change. The first chapter in this unit was Chapter 18, which was entitled Observing Energy. The key takeaways from this chapter were the idea of heat transfer into or out of a system and how we define it based on exo or endothermic, those terms. So exothermic is where you have heat that's transferring from the system to the surroundings, and then endothermic would be when heat is transferred from the surroundings into the system. Now remember, because we are part of the surroundings, we experience this in a different way than the system experiences it. For an exothermic reaction, we experience exothermic reactions as warmth because heat's leaving the system and coming to us in the surroundings. For an endothermic reaction, we experience it as cold because if we go and touch something that is endothermic, that means heat's going into it, meaning heat's leaving us, which is why we feel cold. We looked at the fact that heat transfers between 2 objects of differing temperatures. In fact, heat goes from warmer to cooler, so heat transfers from the object at a higher temperature or substance at a higher temperature to the substance or object at a lower temperature, and heat continues to flow in that one direction until an equilibrium temperature is established. We call that thermal equilibrium. We looked at how heat is involved in phase changes. So in terms of going from solid to liquid to gas, anything moving in this direction because heat's going into the substance to cause that phase change, melting, evaporation, sublimation, all of those are considered endothermic because heat's going into the substance. And then any going in this direction, gas to liquid, liquid to solid, so condensation, freezing, deposition, heat has to be withdrawn from the substance. So if heat's leaving the substance, it's considered exothermic. We also looked at phase changes specifically with water and the varying amounts of heat that is required to undergo a phase change for water. We looked at heat of fusion as the amount of energy required to melt or the amount of energy needed removed from the substance to freeze it, and the heat of vaporization, which is the amount of energy in to vaporize or the amount of energy out to condense, and that's per gram of the substance. So for water, it's 80 calories per gram to freeze or melt, and then 540 calories per gram of water to condense or vaporize. Just in changing the temperature of a substance, though, we have to use something called the specific heat. Each substance has a different specific heat value. Specific heat is the amount of energy that's required by a substance to increase in temperature by 1 degree, or the amount of energy that has to be taken out of the substance to decrease in temperature by 1 degree. So what this is saying, for example, compare water and clay. If we're comparing these 2 specific heat values, whether it's in calories per gram degree Celsius or joules per gram degree Celsius, clay has a lower specific heat value, which means what? It means that the clay only has to absorb 0.33 calories per gram to change the temperature by 1 degree, where water has to absorb 1 whole calorie before it can change its temperature per gram by 1 degree. So that means clay has to absorb less energy, which means that if both of those samples absorb the same amount or release the same amount, then the clay is going to increase or decrease in temperature more drastically than the water will, because it only takes a smaller amount of energy to change the temperature. You should be familiar with looking at different substances like that and comparing what's easier and harder to heat up. So the examples I gave you here was an iron frying pan compared to an earthen pot, which would be like clay. What's easier to warm up, what's harder to warm up based on the specific heat value. By mass, if we're looking at water in a can versus water like in the ocean, the water in the ocean, because there's a larger amount, is not going to heat up as easily as a smaller sample of water because there's just less particles that have to be heated up. So you should be able to do both of those comparisons. In terms of the math, Q is equal to mc delta T, we can use this to quantify the number of joules or calories required to heat up a substance or cool down a substance. So for example, let's take aluminum. If we have 50 grams of aluminum, which has a specific heat, we'll do it in calories of 0.215 calories per gram degree Celsius, and we want to change the temperature by 10 degrees. That doesn't matter if we're going from 20 to 30 or 50 to 60. We just want to change the temperature by 10 degrees. How many calories are required to do that? 50 times 0.215 times 10, and we get 107.5. Now the unit here is calories because that's what my specific heat was in. If I used the specific heat for aluminum in joules per gram degree Celsius, then my value for heat would be in joules. Okay. The last thing that we looked at was the heat involved in phase changes, specifically with water, and the idea that we get if we plot how the temperature changes over time as water goes through phase changes, we get this graph, and we get it for any substance. You start out as a solid. As the substance is absorbing heat energy, the temperature is going to increase, but it only increases until it hits a certain point. And then we notice that for some time, the temperature remains the same, even though heat's being absorbed by the substance. What's happening in that time? The heat's not going into making the particles move faster, it's going into weakening the IMFs of the solid to turn it into a liquid. So during this point in this direction, it's melting. Once it completely melts and you have all liquid, then the heat can go back into making the liquid particles move faster. That's why we see the temperature increase again until we get to the second point where it's going to start boiling or vaporizing. The heat's going to go into weakening the IMFs between the liquid particles to turn them into a gas. Once it's completely gas, then the heat can go back into making the gas particles move faster and the temperature of the gas increases again. These 2 points are important for any substance. This is the melting point or the freezing point. Remember, those are the same value. We call it the melting point here because it's the heating curve. So in that direction, the phase change is melting solid to liquid. But if we had the cooling curve going from liquid to solid, we would call it the freezing point because that's the phase change that's occurring, but it would occur at the same temperature. And this is the boiling point, which also technically would be the condensation point because those 2 phase changes occur at the same temperature as well. It's just whether heat's going in or out. The biggest takeaway is that during phase changes, temperature does not change. The heat that's going into or out of a substance during a phase change is only going into weakening the IMFs if you're going solid, liquid, gas, or strengthening the IMFs if it's going gas, liquid to solid. Other than that, the heat is not going into making the particles move faster. The only time heat will go into changing the temperature is if you just have solid or just liquid or just gas, not at a phase change.